ICP, we're going to work through some in-class examples for gas laws in this screencast. When we're talking gas laws, there are a bunch of different gas laws that are kind of related to one another, and it all depends on which variables that you are looking at when it comes to gases. So when you were doing your reading and watching your puzzles, you probably saw that as volume changes, so does the temperature. So volume and temperature are two variables. We also have pressure. Okay, the pressure affects the properties of gases. And so what we do is we can break them down by what we are looking at. And so for instance, this very first in-class example, a sample of nitrogen occupies a volume of 250 milliliters at a temperature of 25 degrees Celsius. We have volume and temperature. That's suggesting that we are going to be looking at Charles' law. Now, when we're looking at these laws, the important thing to know is that if there's any change in the system, the resulting relationship between variables will be the same as the start. They will be equal to one another. So whatever you start with that relationship, you will end with. Now, Charles' law says that volume and temperature are inversely related. As one goes up, the other goes down. So Charles' law says V1 over T1 is a constant. It's going to give you a relationship. But if there's any change in that, if we change the volume or we change the temperature, it's going to still have the same proportion. Okay? So V1 over T1 equals V2 over T2. Now, sorry, I'm not a math teacher, and so I don't do a whole lot of math annotations, so I'm not used to using Cami this way. Forgive me if it comes off a little rusty, okay? So whenever you're doing gas laws, always identify what you have to start with from the problem. So here we have the volume of 250 milliliters at 25 degrees Celsius. Well, that's our first volume, and we're given our first temperature. Then if we scroll on, we see that we are given a second temperature. We are given 95 degrees Celsius. Okay, so that means that what we are going to be doing is looking for, what we don't have is our second volume. So if the temperature changes, we need to find out what that second volume is. Now you see that I have some scratches over here from when I was working it out in the screencast that did not make the cut. So let me erase this so you can see where the numbers come from. The main thing with Charles' law is that you have to remember that temperature needs to be done in Kelvin. Otherwise, the relationship is going to not come out quite like it needs to be. So whenever you're dealing with temperature in any of the gas laws, actually, you're going to want to make sure that you're dealing with Kelvin. And if you remember, to convert to Kelvin, all you have to do is add 273 to your degrees Celsius. So 25 degrees Celsius equals 273 plus 25, which equals 298 Kelvin. 95 degrees Celsius equals 273, and I'll write this one out in case you're wondering what the heck I'm saying, plus 95, which equals 368 Kelvin. Okay, so these are our T. This is our T1 now, and this is the T2 that we're going to use. Okay, so we know that, let me see if I can scroll over here. Oh, look, I can just bring that over. I love it. We know that V1 over T1 equals V2 over T2. We've identified what we have, and now we can plug in what we have and solve for what we don't have. So V1 is 250 milliliters. T1, 25 degrees, was 298 Kelvin. Equals whatever our V2 is, which is what we don't know, and T2, which is 368 Kelvin. And so now it's just a simple algebraic problem where we solve for V2. So to get rid of the 368 here, we're going to have to multiply each side by 368. So we're going to end up with 368 times, Kelvin, times 250 milliliters over 298 Kelvin equals V2. And now I know I didn't write the 368 on this side because they cancel out. If Algebra is not your strong subject. Just let me know and I can break it down a little further. I'm just running out of room here. So just as a reminder, with units, and like when you did your unit conversions, the units, if it's on the top and the bottom here, they can cancel out. One needs to be on the top, which in this case, 368 is it's the same as 368 over 1. So that's K is on top, and this one crosses off. So we can cross off our K units. That leaves us with 368 times 250 divided by 298. If you plug that into a calculator, do so now. You can pause it right now if you need to, so you can see if you get the right answer. While we're doing that, what I'm going to do is erase over here so I can, while you're pausing it. So what you should see is that you come up with 92,000. We got to keep our milliliters there. We've canceled out our Ks over, well, 368 times 250 is 92,000 milliliters. And then we're going to divide that by the 298 will equal 308.72 milliliters. Make sure you don't forget your units there. Now, since we didn't actually measure this out and we don't know the precision with which they measured it, you don't have to worry so much about significant figures. And on this assignment, I'm going to be looking at your work and not worrying about significant figures. Because if you can see over here, 308.72 definitely doesn't have the two significant figures that were mentioned up here. But I can see if you know what you're doing a little bit better. Okay, so that's an example of Charles' law. I'm going to pause it here. I'm going to stop this video here and I'm going to upload it as Charles' law. And then I will make a separate video for Boyle's law, question B, and a third video for the combined gas law, question C.